Look at this consumer pickup truck. It weighs over 7,000 pounds, yet accelerates from 0 to 60 in 2.7 seconds. Then there are four-door electric luxury sedans clocking that same sprint in under 2 seconds. The automotive industry has quietly entered a phase of extreme acceleration. Numbers that engineers previously considered physically impossible for street-legal tires to handle are now standard off the showroom floor. The absolute fastest vehicles on the road today have completely divorced from the lightweight combustion-powered track machines that used to define automotive speed. To understand how we got here, we have to look at the European Union's looming Euro 7 emission regulations, taking effect between 2026 and 2027. This chart illustrates the strict new requirements. Alongside a sharp plunge in allowable nitrogen oxide limits, the regulation introduces a 10-year durability mandate. To enforce that curve, vehicles must be equipped with onboard monitoring systems continually transmitting emissions performance in real time. For automotive manufacturers, these severe restrictions effectively signed a death warrant for the traditional, fire-breathing V12 engine. Government intervention created a massive engineering bottleneck. Car makers had to build drastically cleaner cars, but they still needed to deliver the visceral speed their high-paying consumers demanded. The solution was a categorical shift away from standard supercars into a new ultra-exclusive tier of engineering, the hypercar. In the hypercar world, hybridization serves as a ruthless engineering workaround to unlock extreme acceleration while satisfying regulators. Look at this graph tracking a standard combustion engine's power delivery. Notice the distinct dip right here. That is turbo lag, a gap in power during acceleration. By introducing an electric motor, engineers provide instantaneous torque that perfectly fills that mechanical gap. This combination forces the vehicle to rely on the dual strengths of both systems, pairing the high RPM scream of a gas engine with the violent, instant push of electricity. Modern hypercars routinely utilize multiple alternating current motors alongside massive V12 engines to reach combined outputs well over 1,000 horsepower. Integrating these battery packs gives manufacturers a distinct regulatory advantage. It allows the vehicle to pass strict low-speed urban emissions tests by crawling along on silent electric power. But the moment that same car hits an open road and engages the combustion engine, it unleashes a sub-2.5-second sprint to 60. The traditional combustion supercar didn't die. Lawmakers essentially forced it to evolve into a hybridized cyborg to survive. Euro 7 regulations accidentally weaponized electric compliance technology, handing engineers the tools to create the ultimate speed enhancement. That speed comes with a physical consequence. The historically lightweight, agile design of the original supercars has been replaced by the immense, bloated mass of modern performance vehicles. Strapping heavy lithium-ion battery packs and electric motors onto a luxury frame incurs a massive weight penalty. Today, you have modern AMG sedans weighing in at nearly 6,000 pounds that can still manage to hit 60 miles per hour in 2.6 seconds. Managing that terrifying amount of momentum requires moving away from pure mechanical engineering. These cars now rely heavily on software-defined vehicle systems just to keep them on the road. The physics of speed dictates an unavoidable reality. Launching nearly 3 tons of mass at sub-3-second speeds places devastating stress on the vehicle's physical contact points. The immense weight and violent electric torque of modern hypercars chew through brake pads and tires at a highly accelerated rate. Those discarded tire and brake particles have quietly become a major source of microplastic and particulate matter pollution in densely populated areas. The Euro 7 framework is actually adapting to this. It is the first regulation in history to specifically target these non-exhaust emissions. The hybrid architecture, designed to eliminate tailpipe gases, shifts the environmental burden to the road surface, increasing particulate runoff as tires struggle to manage the extreme weight. The high-performance machine now operates on a software-defined high-wire act, balancing immense electrified weight and tire physics against an ever-tightening legal landscape.